I'm going to share with you some research today that's part of my master's thesis, which will be completed in about 2 months' time. And I'm concerned with questions relating to how we utilize global wind and solar resources, particularly in the electricity sector. I just want to set the context for this work by introducing 5 numbers that are going to be quite relevant over the next quarter century. Because over that period, it's expected that globally we'll install nearly 6 terawatts of generating capacity, requiring something like $17 trillion in infrastructure investments. Now, if this expansion follows current trends in fossil fuel use, it's expected that the power sector will increase emissions by about 60%. If alternatively governments succeed in meeting commitments made to date, that increase will be only about 14%, but even this pales in comparison to something that might be required to reach a safe or prudent stabilization target. Now, it's important to keep these numbers in mind because we just need to be really familiar with the fact that the scale of the challenge, particularly in the power sector, is absolutely massive. In fact, over the next quarter century, the task facing us is something equivalent to reducing emissions from the baseline level in such a way that it's basically equivalent to taking every fossil fuel power plant on Earth today and replacing it with a clean technology alternative. Now, this context leads to sort of a meta question that sort of underpins a lot of my work, and the question goes something like this. Imagine that you have $100 billion, and the question is, how do you invest that $100 billion? You can invest it anywhere in the world in any technology in the power sector, but the one goal you have in mind is to reduce greenhouse gas emissions in as cost-effective a manner as possible. Now, the problem is that this is actually an exceptionally complex problem. And if you think about it, the technologies, particularly the renewable technologies that we're most interested in, are going to be highly dependent on space and time. I mean, a wind turbine, the performance varies not just tremendously across space, but across seasons and even across hours within each day. And matching that with consumption is an extremely complex issue that we simply can't look at casually and answer. Now, of course, we have complex allocation problems in a lot of different sectors, and we often solve them by trying to model reality in such a way that it can inform our decisions. The problem is that although we have a lot of large-scale energy models out there, they're really not equipped to deal with these with problems that relate to spatially explicit technologies. In fact, they come out of the economics literature, they're sectoral in nature, and they ignore spatial implications altogether. And we do have a very small number of small-scale models that are actually designed to take into account spatial considerations, but the number of models out there that do this, or you can count them on one hand in the world, they're always limited to a particular geography, and so they can't provide answers to really global-scale solutions, or problems, excuse me. So my proposal has been to develop a spatially explicit power and transmission model, which I also call Sexpot, which is the catchy name for it. Now, Sexpot is a model which is designed specifically to address the shortcomings in conventional models, and in particular it's designed to run at high spatiotemporal resolution. The initial version of Sexpot that I'm building right now will incorporate wind technologies as well as rooftop and utility scale photovoltaics and concentrating solar power, which is a thermal power generation technology. The model is being written in the R programming language, which has a number of advantages. It's very flexible, and it allows me to combine functions and packages and statistical techniques across spatial statistics, atmospheric physics, engineering, statistical model fitting. It's really a good language to be building something like Sexpot in. And this is the basic layout of the Sexpot program. I'm not going to go into the technical details today, we just don't have enough time. But I just want to make you familiar with the idea that basically Sexpot is taking a large amount of environmental data, spatially explicit, temporally explicit data, most important of which is hourly wind and solar parameters from NASA's GEOS-5 reassimilation model. Now it's running those through processing algorithms to generate spatiotemporal data within Sexpot. This is information that I'll show some examples of it in a couple minutes, and this is really interesting data that has yet to be produced and that Sexpot enables us to work with now. We combine this information with assumptions about fuel prices and capital costs and run it through an optimization process, and what we get out at the end is actually spatially explicit results that actually show us across space and time where we want to deploy certain technologies to reduce emissions. Today I just want to show you some examples of data that's been created within Sexpot showing the potential for some renewable energy technologies across space and time and predictions of electricity consumption. So you should be getting a movie coming across now, and this is showing modeled wind turbine generating efficiency for every hour of the day for a representative day for 6 months out of the year. You can see it's going through the time steps there. This is done by taking wind speed data from NASA's GEOS 5 model and basically extrapolating it through the planetary boundary layer to the hub height of turbines, running it through an engineering model, and then making adjustments, for example, air density and that sort of thing. This is really the highest resolution look we've had at wind power generation potential, really in any research yet. We can do the same sort of thing with solar technologies. Looks to me like the video is lagging behind maybe a little bit, so I'll let it catch up. Okay, so now you're looking at utility scale photovoltaic generation. Same idea, except here we've added something which is we've actually screened out areas of the world where you simply couldn't put the technology. And I point that out because within Sexpot is a very high resolution terrain screening algorithm for all the technologies that utilizes very high resolution 300-meter land cover data from the European Space Agency. And this allows us to actually go in and say, well, look, you couldn't put the technology here because it's too steep, you have land cover, you have population centers nearby, to get a more realistic picture of where we can actually put technologies. And then finally, we need to match this production side information with information from the consumption side. So this is a model of electricity consumption hour by hour, and this is done by taking actually about 200,000 hours of actual electricity consumption data for markets in Europe and Australia, matching it with the exact same weather conditions for each hour, and then fitting a statistical model to it that allows us to predict electricity consumption as a function of meteorological conditions. This is what the previous movie would look like if we took a single grid cell over Beijing and simply looked at the predicted electricity consumption over the course of a typical day for January. And then, of course, we can do that for each month. This is really, it's very hard to get electricity consumption data like this. In fact, if anyone knows of where I could get more data, particularly in developing economies, that would be quite useful. Now, the big challenge is to take all of this information that's being generated on the production side and the consumption side and relate it to each other via transmission, which is the spatial link, in order to generate results that are actually useful. And this is exceptionally complex when you consider that we have thousands upon thousands of potential production sites, multiple technologies, and thousands of potential consumption sites, and then we have to think about each hour of the day for each of those sites. So a very large optimization problem faces us, and linear programs are ideal for that because they're able to deal with large-scale problems very efficiently. Now in Sexpot, this is the part that the final part that I'm working on now, and that is to develop a linear program that allows us to combine all of this information into a single, basically a single statistical process that allows us to ask Sexpot, if I wanted to reduce emissions by a certain amount, how would I allocate technologies across space in order to minimize the cost of meeting electricity demand subject to my emissions constraint? Now, when you start thinking about what Sexpot's really doing, you realize that there are actually a lot of applications because a lot of the research questions, a lot of the phenomena we're most interested in are spatially explicit, and we can tweak Sexpot to answer questions in a lot of different domains. One I mentioned, of course, the one that I'm most interested in, is how to most efficiently distribute energy subsidies on global scale. This could be World Bank clean investment financing, this could be CDM credits or money for carbon offsets, or even within large countries like India and China, how do we distribute those resources across our own terrain? And then secondly, every technology is to some degree spatially explicit. Wind and solar are exceptionally so, but also technology like CCS, or carbon capture and sequestration, which in conventional energy models always comes out as quite prominent in the energy mix. But it may be that that's only because we never treat it in a spatially explicit manner. We never consider the fact that the geologic formations where we would like to store carbon aren't actually located or might not be located near where we're actually producing it. And we need to incorporate that spatially explicit nature into the modeling itself. So these are some of the uses that a model like Sexpot might have down the road. Like I said, the model is currently being completed. About 2 months' time, we should have a thesis done. And I think I should be within time, so I'm happy to answer any questions or clarifications that anyone would like.